right, we are in the middle of learning about diffusion. Diffusion is what happens in all kinds of systems, but we're focusing pretty heavily on diffusion in solids. And before I get started, there's just a couple of equations I want to bring back to our forebrain. The first of these equations also includes a term we call flux, and we give it the symbol J, and it has, of course, units of mass per unit area per unit time. So we can write that as mass per area time. And this is why it often has units of something like kilograms per meter squared second, just as an example. So that is flux. And Fick's first law tells us that the flux is directly proportional to the diffusivity, or the diffusion constant. It's directly proportional to the concentration gradient, which is the driving force for atomic motion. And the direction of the atom motion actually goes in the opposite direction as the concentration gradient, which is why we have a negative sign. So that's a reminder. And then let's see if that's all we need to do this problem. So in this problem, I'm going to begin by kind of drawing a little bit of sketch. So we see that we have carbon being allowed to diffuse through a steel plate that is 8.4 millimeters thick. So if this is the plate, so this is the steel plate, I'm shading it in, steel plate. What we've just been told is that the distance, the sort of cross-sectional, the distance from here to here, if I called this x, that distance is 8.4 millimeters. And I'm going to be super smart here and point out that the units I'm seeing elsewhere in the problem have meters in them. I can see meters here and meters there. So I'm going to kind of immediately change that into meters. So that will be 0.0084 meters. So if this is distance 0, this is distance 0.0084 meters. All right, so that's my sketch so far, and so we have carbon diffusing, all right, and it's telling us that there's two different concentrations at the two different faces. So this is one of the faces right here. I've only drawn it like a line, but if we were to draw it in 3 dimensions, you'd see that there's some cross-sectional area to this plate, and so we're basically thinking about carbon, diffusing through here, right? And now I got to clean up my diagram because it's too messy for me, but I'm trying to point out that, this is why flux occurs across an area with respect to time. So I'm going to redo my diagram, make it nice and careful and neat. Instead of drawing a plane, I'm just drawing a line. So x goes from 0 to 0.0084 meters. And the problem statement is telling us that the concentration at the left face, I'm going to call it the left face, is 0.667 in units of kilograms of carbon per square meters. So I'm going to write kilograms per cubic meters, and that on the other face, it's a lower value, and I've put it at a lower value. So if this is my concentration, and then I'm plotting that as I go, upwards, the concentration on the other side of the plate is only 0.188 kilogram. So over here, we would see, if we read off what the concentration was at this distance, it would be 0.188. So and then we're told that these concentrations are maintained constant, and we can, and so what that will eventually mean, right, is that we have steady state diffusion, and that we can approximate what's going on with just a linear line working our way across it. So on the left side, we have a high carbon concentration, and on the right side, we have a low carbon concentration. And I've drawn a picture like this because it helps us to understand what the concentration gradient is. So if I call this point A and I call this point B, the dc dx, right, which is another way of writing that when things are at steady state like this and it's a nice linear line, is that we have the change in concentration with respect to the change in distance. And another, and the way to work out what that is to take the concentration at one of the points and subtract it from the concentration at the other point, while similarly doing the same thing with the distance. And so in this case, what we are going to see is that we will have 0.188 minus 0.667 divided by 0.0084 minus 0. The units of concentration are kilograms per cubic meter, and then the units at the bottom in distance are in units of meters. All right, and when you plug these numbers carefully into your calculator, you will see that this equals a negative 79.22 kilograms per meter to the fourth. All right, so that is our dc dx. Our dc dx is equal to that value over there. So if I can change color, what I've just calculated is this part of the equation right there. And I'm just going to kind of look back because I'm like, what are we trying to find here? So carbon is allowed to diffuse. The concentration of the carbon is this. If the pre-exponential and activation energy are these two values, calculate the temperature in Kelvin at which the diffusion flux is 3.2 times 10 to the 9th kilograms per meter squared per second. All right, well, we're definitely going to need one more equation, but let's just kind of, so we are told what the diffusion flux is, right? So relative to this first equation, we know J, we know dc dx, and so we can calculate what D is, and all right, and so that's going to be our next step, but I'm going to kind of explain why, right? So why we want D is because D, this is the second major equation in this chapter, and we're going to use it all the time, that the diffusivity at any temperature within a range of data is equal to, this is called the pre-exponential constant. So I'm going to circle that and make it, I'm going to highlight it green, or whatever this color is, orange. So that's what the pre-exponential constant is. And then I'm going to use a different highlighter and make the activation energy. That's what Q is, all right? So those are the words associated relative back to the equations. All right, so D equals D naught E, or exp, sometimes we say E and then we write it like that. So E to the Q over R times T, where R is 8.314 joules per Kelvin, and T is in Kelvin, which is equal to 273 plus degrees C, right? Okay, so our overall strategy, once we have D, we'll put it into there, and we know our D naught, we know our Q, we know R because it's a constant, and we will be able to figure out the temperature. So we've got a few steps to go, but and I'm going to kind of be scrolling back and forth from here to the next page. And so let me just kind of pull down some of the stuff that we already know. We know that dc dx is minus 79.22 kilograms per meter to the fourth. We know the flux from the problem statement is 3.2 times 10 to the minus 9 kilograms per meter squared second. And so we also know the formula, and I'm gonna rearrange this formula a little bit and solve for D. And so in doing that, we're going to see that minus J divided by the concentration gradient, dc dx, is equal to D. And so now I should be able to just plug in those two values so we will have a minus 3.2 times 10 to the minus 9 kilograms meter squared per second divided by minus 79.22 kilograms per meter to the fourth. And when we solve for D, we will get a positive, and I'm going to put a bunch of sig figs in here. I believe it's 4.03955 times 10 to the minus 11, and what I'm going to be left with are meters squared per second relative to the units, and that is the correct units for diffusivity. So we have found we found D. All right, so let me call this equation A, right? So we used equation A to get D. And now I'm going to use equation B up here, all right? And I'm going to rewrite it so I can get us kind of all on the same page here. So D equals D naught times E raised to the minus Q over RT. By the way, sometimes you will see this written as D equals D naught exp minus Q over RT. These are the same thing, but when you're looking for the function in your calculator, you're looking for the e to the minus function. And so remember, we were given D naught. It was, the pre-exponential was 6.5 times 10 to the minus 7. We were given Q, which was 82 kilojoules per mole. R is equal to 8.31. And I am looking for my formula sheet to make sure I'm in the right units. Hold on. So this is where we got to be careful with the units. Yeah, the units of 8.31 are joules per mole Kelvin. And as you know by now, I'm hypersensitive to units, so I'm going to immediately change Q to be 82,000 joules per mole. And I'm going to use that one. All right, so given all these things, right, and the fact that we now know D, right, so we're given these three things and D, when we look at the formula, we see that and I'm gonna do this in red, we know D, we know D naught, we know Q, we know R, right? So we're solving for T. So we're going to need to do a little bit of manipulation with this formula. So let me begin to do that. So I'm going to divide by D naught. So D over D naught, and I'm going to put in the real values. So that's going to be 4.03955 times 10 to the minus 11 meters squared per second. I'm going to divide by 6.5 times 10 to the minus 7, and I believe that was in meters squared per second. Let's assume it was meters squared per second. And that will then equal E raised to the minus, so now we got to put our Q in, 82,000 joules per mole divided by 8.31 joules per mole Kelvin, and here's where we have our T in Kelvin. So since we're in joules per mole, and our answer will come out in Kelvin, all right? So what we want to do now is just be super, super careful in plugging these into our calculator. When I do this division, I get, I'm keeping these more significant figures in my calculator, so I'm not writing them all down, they're in my calculator. So d over d naught equals that value, and that equals e raised to the, and I've done some simplification, 9867.6 over T in Kelvin. Okay, so now that's where I am. Okay, that is equal to that, and so I am now solving for T, of course, right? So what I'd like to do is take the natural log of that, and then that will equal the natural log of that. And what I will get when I take the natural log of that little tiny number is I will get minus 9.860, and that will equal, so the natural log of E raised to that number is just that number, right? So we will get 9867.6 divided by T. So now I'm going to multiply both sides of the equation by T, and I think, do I have any more room? Yeah, so let's multiply by T. So I will get, this comes to 9, both sides have a negative sign, so they're going to get wiped out, so we'll say 9.860 T equals 9867.6, and now I'm going to divide by 9.860. T equals 9867.6 over 9. Yeah, is it 680 or 860? 9 point, I have a transposing error. I'm going to insert a little 6 here. 9.6860 is what when I'm looking back in my notes. So I apologize for that. And 9867 divided by 9.6860, and that is equal to 1018.8 degrees Kelvin. All right, so that's kind of where we ended up, and that is the final answer. If the problem statement asked for it in degrees C, we would, of course, convert it to degrees C, but it asked for it in Kelvin. So that is our final answer given these initial values. And again, I don't know, to summarize, if I could, in general, for these kinds of problems, we're using Fick's first law, which has diffusivity in it, and it has a concentration gradient, right? So we use Fick's first law, and then the other thing that often gets involved is the fact that D changes with different temperatures according to this principle. So, become familiar with both of them, and especially become familiar with solving equations like this. And I'd like to end it here. Thanks very much.